Hey class, so today we're going to be talking about balancing chemical reactions. Now, this is lesson 8 of the chemistry unit. We already covered 7 previous lessons, so let's get started, okay? So the big idea today is there are various strategies involved in balancing chemical reactions, and you need to balance a chemical reaction for calculation purposes. Now, we talk about calculation purposes. That doesn't really have much meaning this year in Science 10, but that will when we get to Chemistry 11. So now, before we get started on balancing, we got to first talk about what these conservation laws are in chemistry. These conservation laws in chemistry are very important because they allow us to do a lot of our calculations, especially when we talk about balancing. So, there's something called systems. And there are really 3 types of systems that we deal with. There's what we call an open system. There's what we call a closed system. And there's one that we call isolated system. Okay? So these 3 are 3 different types of system. An open system means that there is an exchange of substance and energy with surroundings. Okay, now what is the surroundings? Well, first of all, we know what the system is. The system is what we are studying, what we are currently studying. So in this case, if we are studying a chemical reaction, the system is a chemical reaction. The surroundings ain't it's outside of that. So an open system is where there's an exchange of substance and energy with the surroundings, such as, for example, a cup of water. If you have a cup of water without a lid, that is an open system because you could have, for example, water evaporate. That's a substance. But you could also have that water heat up or cool down. And that's a change of energy. A closed system is where there is only exchange of energy. Because a closed system is such as, for example, one that, for example, has a lid. If you have a lid, that substance piece is no longer getting exchanged, but instead there's still energy change. Such as, for example, you can still heat up that cup of water even if it has a lid. The last example is isolated. An isolated system is where there's no exchange. This is one that is, for example, a thermos. A thermos is a container in which you usually have a lid that allows there's no evaporation of any substance, but it's also insulated. And what insulated means that is that it usually tries to keep the system isolated, and it doesn't have a transfer of energy. So it takes a long time for that substance to cool down. So we're going to talk about in terms of systems. So the conservation laws of chemistry are these. There is 4 different laws we're going to talk about, okay? So conservation laws. Conservation laws. Okay? So we talk about conservation laws, there is the conservation of mass. Okay? Mass just means that in this case, because mass is conserved, total mass from start to finish of the reaction does not change. Okay, so that means when a reaction progresses, the mass will not change. The second law is electrical charge. Okay, and this one just means that the total charge does not change. So total charge does not change. Okay, so for example, if you talk about conservation of mass, you could say that you started with 120 grams of something. After reaction, you should still have 120 grams if it is actually only for isolated systems. Okay, so if it's an isolated system, conservation laws will be applied. Because if it's an open system, then mass will not be constant, it will not be conserved. If it's a closed system, then the next law will not be conserved because the next law is the conservation of energy. And this is where total energy does not change. Okay. So energy can only be transformed but not changed. So these three laws here are very important, but the one we're going to use to help us balance chemical reactions is the last one. And this one is atoms. The conservation of atoms. And this is where total and types of atom does not change. So what that means? Well, that means that if you have 7 oxygen atoms, then you should finish off with 7 oxygen atoms as well. So that's what the conservation of atoms is. So we're going to use the conservation of atoms to help us balance. But before we get into any balancing, we got to know some important terms so that when we are stating these in the lesson, you know what they mean, okay? So the first one is, what is reactants? So a reactant is your starting chemicals. Whatever chemicals you are starting with is what we call reactants. Well, if we have starting chemicals, then we must have our resulting final chemicals. And those are called products. The products are our resulting chemicals. The last term I want you to know is very important. This is like the one from algebra. It is coefficients. Now, a coefficient in algebra is the number you put in front of a variable to tell you how many of each variable you have. And it's the same in balancing. It's the number in front of a formula to tell you how many of each molecule you have in front of a formula to tell number of each molecule. So these are the 3 important terms that we're going to use that allows us to balance. That when I talk about reactants, you now know what that means. If I talk about products, you know what that means. And if I talk about coefficients, you know what that means. And I'm going to flip the page now. So if you need more time to write, just pause this video and then you can restart it whenever you are done. So, we're now going to talk about strategies. What are some strategies to balancing chemical reactions? Now, these strategies work for me. They are strategies that I've been using for a while. And you might have different strategies that work for you, and don't feel like you need to stick with the strategies that I have shown you. Because if you have other strategies that work for you, I would say continue using them. So, the first strategy that we always want to do, and this is the one that is pretty much universal, is what you want to do is, but using coefficients, balance what appears once on both sides of the reaction. That means it appears once on the reactant side, it appears once on the product side. Okay, so now here's a little strategy, here's a little hint. These are usually the metal. So if you're talking about a ionic reaction, this is usually the metal that you're going to be balancing first. But what if there's some reactions that don't have metals? If there's no metals, then you always want to balance hydrogen and oxygen last. The reason why is because you usually end up with hydrogen or oxygen with multiple of them on either side. And this is the reason why you always want to balance them last. So we're going to go through these steps one at a time when we balance our examples. Number 2. What you want to do after you do this is balance what is attached to what you just balanced in question or in step number 1. Balance what you just, oops, my bad. Balance what is attached to what you just balanced. What is attached to what you just balanced in step 1. Okay. So, if for example you just balanced sodium in step 1 and there's a chlorine attached to the sodium, such as sodium chloride, then you want to balance the chlorine next. Okay. Now here's step 3, the best step of them all. Repeat step 1 and 2 for other chemical you haven't balanced yet. Step 1 and 2 for the other chemicals. Okay, so you want to make sure that you are basically doing this back and forth, step 1, step 2, step 1, step 2, until you balance everything. And always remember that you always want to make sure you keep hydrogen and oxygen last to balance. Okay, now here are some strategies, some notes, okay, that I want you to keep track of. Okay, the first one I want you to do is you do not need the number 1 in front as a coefficient. Just like in algebra, you don't ever put 1. You do not need to write 1 as a coefficient. Okay. The second note I want you to do is balance polyatomic ions as one whole group. Balance polyatomic ions as one whole group. So, for example, if you have SO4, do not balance sulfur, the S by itself, and the oxygen by itself. No, balance it as if it's one whole group, SO4 itself. What you can also do is for ionic reactions, such as for example acid-base reaction, write water as HOH. The reason why you want to do this is because you're actually going to see that a lot of times you're going to have hydrogen coming from one of the ionic compounds and OH coming from the other, and that's what water will become, HOH. It allows you to balance the OH, the hydroxide, as a polyatomic ion as one group. Now there's one more strategy that I didn't go over with you, and it's called so if you want to write this number 4, it's called the double odd even rule. Okay, I'll show you an example of double odd even rule in a bit, but basically what this means is you double all coefficients when you have an odd and even value. Okay, and I'll show you what that looks like in an example in a bit, okay? So don't freak out too much if you don't know what the double odd even rule is. We're going to do about 2 examples to get you comfortable with it, okay? So, we're now going to talk about this with a few examples, okay? So we're going to do a few examples just so you're clear. So, let's get the first example. The first example is you have H2S plus PbCl2 will give you PbS plus HCl, okay? So you have hydrosulfuric acid plus lead 2 chloride. When it reacts, it's going to give you lead 2 sulfide and hydrochloric acid. So what do you do? Well, the first step you should always want to do is balance what appears once on both sides, and this is usually the metal. So you look at this, you see that you have a metal in lead. Hydrogen in this case actually acts as a metal, but let's do lead first. But once you get comfortable with this, you actually do hydrogen as a metal as well, because hydrogen here, because it's an acid, acts as a metal. So what do? Well, you look here. Pb, lead. There's one lead here and there's one lead here, that's already balanced. So hey, that's a good step right there. But now step 2 is where you want to go balance what is attached to what you balance in step 1. So in step 1, we balance the lead. So we want to balance now what's attached to the lead. So as you see, this lead is attached to a chlorine. So I want to balance the chlorine next. Or you could balance the sulfur next if you wanted to on this side. But usually I like to go left to right. So you have 2 chlorines in the reactant side. You only have 1 chlorine in the product side. How do you balance? Well, you use coefficients to help you balance. You do not put a 2 here because that is wrong. You'd never ever want to do that because that changes the whole chemical. Instead, you use coefficients like this to show that now you have 2 hydrochloric acids, 2 hydrogens, and 2 chlorines that are balanced here. That's what the coefficient represents. Now, what you want to do now is you want to balance and repeat step 1 and 2 by doing the next one. So in this case, again, we said that hydrogens act as a metal, so let's balance hydrogen. Here you have 2 hydrogens. Well, guess what? By putting the 2 coefficient here, you have 2 hydrogens there as well. Last but not least, you have a sulfur. As you see, you have 1 sulfur here and 1 sulfur here, so this is now balanced. So, now moving on to the next question, you could try pausing the video to practice, but what you want to move on to now is the what we call combustion reaction. A combustion reaction is where you always have a hydrocarbon, which we learned previously. Reacting with oxygen gas gives you carbon dioxide and water. So let's balance this one. So the first step is you always want to balance oxygen, hydrogen last. So this is the reason why. If you see you have 1 oxygen on the reactant side, that's fine. But you look at your product side, you have an oxygen here and an oxygen here. That's 2 different types of oxygen. So that's why you want to balance them last. So, if you look at here, you want to balance the carbon first. You have 3 carbons on the reactant side. You have 1 carbon on the product side. So you need to put a 3 coefficient right in front of the CO2, the carbon dioxide. Because oxygen appears twice, you want to balance the hydrogen next because there's only 1 hydrogen on either side. So as you see, you have 8 hydrogens here, but only 2 hydrogens in the product side. So you want to balance and put a 4 in front of the water to balance out the hydrogen. Your last step now is to balance the oxygen. You have 3 times 2 oxygens in CO2. So in this case, that means you have 6 oxygens here. On this side, you have 4 times 1 oxygen here. So that means you have 4 times 1, so you have 4 oxygens here. So in total, you have 10 oxygens. So that means you need 10 oxygens in the reactant side. What times 2 gives you 10? And that number is the number 5. So as you see, if I erase these 2 in the bottom, this is the balanced version of this reaction. That means what's actually occurring is you're going to have 1 molecule of what we call propane right here. Reacts to 5 molecules of oxygen, gives you 3 molecules of carbon dioxide and 4 molecules of water. Now, our last example here before I move on to a rule called double odd even is one that involves polyatomic ions. Because PO4 is a polyatomic ion, hydroxide, OH is a polyatomic ion. So what we want to do, well, this is an ionic type of reaction, it's an acid-base reaction, so we're going to write water as HOH in this reaction. Notice how we didn't write water as HOH in this reaction because it's not an ionic type of reaction. So this is HOH now. So as you can see, you have an OH group here, and you have an OH group right here, so that allows you to balance this a lot easier. So let's start. Let's start by balancing our sodium. That's our metal. We have 1 sodium here, we have 3 sodium here. What do we need? We need a 3 coefficient in front of this to balance out our sodium, because now we have 3 sodiums here and 3 sodiums here. Well, what's next? You want to balance what's attached to the sodium, which is OH. So balance the O and H together. I know we said that you want to balance the hydrogen and oxygen last, but in this case, because this is OH, it doesn't really follow that rule. So in this case, you have 3 hydroxide groups because that 3 is affecting the whole hydroxide. So you have 3 hydroxide groups there on the reactant side. What do you need on the product side? You also need a 3 in front of this because now you have 3 hydroxide groups as well over here. Okay, let's go balance the hydrogens next. You have 3 hydrogens over here on the reactant side. You have 3 hydrogens now on the product side. It's completed. So that's balanced. Well, what's attached to hydrogen on the reactant side? It's a phosphate, PO4 group. You have 1 phosphate group here. Over here, you also have 1 phosphate group. As you see now, everything is now balanced. So these 3 examples are going to show you how to balance using the first 3 rules. But now I'm going to show you an example that deals with the double odd even rule. So let's try this example. So if you have some space in the bottom of your notes, I want you to write, just by adding 1 extra carbon, 2 extra hydrogens, this double odd even rule comes into play. So we're going to write C4H10 plus oxygen gas still will react to form still CO2 plus H2O. Okay, so here's a reaction. This is where we're going to use the double odd even rule. So, again, we want to balance our carbons first. You see you have 4 carbons on the reactant side, so you must put a 4 in front of your product side carbon in the carbon dioxide to be balanced. You have 10 hydrogens over here, you have 2 over here, so you got to put a 5 water molecules there to balance this out. Now you want to count the oxygens. So here, as you see, you have 4 times 2, that's 8 oxygens here, and then plus another 5 times 1, so that's another 5 here. You have 13 oxygens. What times 2 gives you 13? Well, a lot of you are going to go, this means I have to multiply maybe like something like 6.5 or 13 over 2, right? And you can do that. You can say this is 13 over 2, but we can't have half an oxygen molecule. So you got to get rid of this lowest common denominator somehow. And some people would multiply everything by 2. But I'm going to get rid of this step and just call it the double odd even rule. Because right now you have an odd number of oxygen on your product side, but you have an even number of oxygen on your reactant side. What do? You use the double odd even rule, which means that you now take this whole reaction, except for the oxygen, and multiply it by 2. And by doing that, what's going to happen is your reaction's going to now, everything you just balanced is going to multiply by 2 except for that oxygen, because you haven't balanced that yet. So what happens here? Well, you're now going to have 2 butane molecules. You have 2 C4H10s. Plus, the O2 is still unbalanced. We haven't touched that yet because we haven't balanced that previously. But you're now going to have, in this case, 2 times 4 carbon dioxide. That becomes 8 carbon dioxides. So 8 CO2s. And then 2 times 5 water molecules, which means now you have 10 water molecules. So now, if you take a look at this, everything is still balanced from previously. You still have 2 times 4, that's still 8 carbons here, 8 carbons here. 2 times 10 hydrogens, you still have 20 hydrogens here, and you still have 20 hydrogens here. But this now allows you to balance those oxygens a lot easier. Why? Well, now you have 16 oxygens here and 10 oxygens here. That means you have 26 oxygens. As you see, it really just means you doubled this 13 to 26. Well, what times 2 gives you 26? And that number is 13. So instead of writing a fraction now, you now have whole numbers. Because when we balance, we got to make sure we balance all of our numbers with whole numbers. That's a rule we got to make sure we have. So, for homework, I want you to practice balancing in the homework provided. But other than that, this is our lesson for balancing chemical reactions. Feel free to email me at any time or to go ask me any questions, and I will gladly answer it. So make sure again you stay safe and healthy, and I'll see you soon.